In this video, we will be going over the uses of influence lines, which include moving loads and uniformly distributed loads. The first problem reads, for the beam shown, compute the maximum positive and shear moment at B, as well as the maximum negative moment at B due to the series of moving loads as shown. We will start off by doing the maximum positive shear at B. So the first thing we want to do is to draw the shear diagram at B. You can go ahead and label this A, B, and C. And then we just have to go ahead and use the rules that we know to draw the shear at B. So we know that the shear at B is going to be 1 unit, and the rest of the lines will look something like this. In order to find this point and this point, we have to look at the lengths of this. So we know for this point, we will have to do 20 over 50 because 50 is the 20 plus the 30, and then this will give us 0.4. So this is 0.4. And then since we know that this whole thing is 1, we know that this will be 0.6. Or as well, just to check, we can do the 30 over 50, which will be 0.6. So now we can go ahead and write the slope for this line to be 0.6 over 30. And this will be 0.4 over 20. Now we can focus on the moving load. So we can go ahead and draw the moving load here. Since we want to find the maximum positive shear, we're going to have to move this moving load somewhere where it has the maximum positive shear, which is the maximum positive shear. The positive shear is this part, and this will be the negative part. So we will move this here, and we have to take note at the distances in order for us to calculate the maximum positive shear at B. We can go ahead and draw where the loads are. So this will be here, here, and here. Then we can go ahead and calculate it. So since we know that this part is negative, the first load is the 8K, so this would be negative 8 kips times the slope, which is 0.4 over 20, times this distance here is 6 feet, because this distance is 14 and this is total is 20, so 20 minus 14 is 6 feet. And then the next load is this one, so this will be, we're going to be adding this one, so this would be the 32 kips times the slope, which is 0.6 over 30, times the distance, which will be 30 feet, because this distance here is 30 feet. Then we will add the other one, which is this load. We will do plus 32 kips times the slope, which is 0.6 over 30, times the distance, which this distance is going to be 30 minus 14, which is equal to 16. So this is 16 feet. Multiply this by 16 feet, and we get negative 0.96 plus 19.2 plus 10.24, which will give us a total of 28.48 kips. So then the maximum positive shear at B is equal to 28.48 kips. And this would be the answer for part 1. And now we can move on to finding the maximum positive moment at B. So we will start off by doing the same thing, which is drawing the moment diagram at B. So we can go ahead and label this A, B, and C. To draw the influence line for the moment at B. we have to do, it will look something like this, with this being 1 unit, and as well as this will be 1 unit. So to solve for this point, we have to use parallel lines and angles to solve for that. We will call this angle A, angle C, and this would be angle C, and this would be angle A. And this is angle A, and this is angle C. So we know that angle A is equal to, well, we can label this D, and so this will equal to dB over 20, because this distance is 20. This distance is 20, and this distance is 30. So then angle C is equal to dB over 30. So then if we add dB over 20 plus dB over 30 and equal it to 1, because we know that, as I mentioned before, this is 1 unit. And then we go ahead and solve for it. So it will be 30 dB plus 20 dB over 20 times 30 is equal to 1. We go ahead and solve for dB, and we get that dB is equal to 12. We can put the dB is equal to 12 here. We can go ahead and put the slope here is equal to 12 over 20, and the slope here will be equal to 12 over 30. So now we can go ahead and draw the moving load. So since we want the maximum positive moment, we're gonna have to implement the same idea, which is to put this moving load over the maximum positive moment. So this will be something like this. It will be placed here. So then we know that this load will be in this area, and this load will be here, and the 8 kip load will be here. So now we can go ahead and calculate it. So we will start off by doing the 8 kip load, and the 8 kip load is positive. So we will add the 8 kips times the slope, which is 12 over 20, times the distance. This distance, since this is 14, as seen here, and the distance is 20 here, so we know that this distance will be 6 feet. So we will multiply that by 6 feet. We will then add the following load, which is the 32 kip times the slope, which is 12 over 20, times the distance, which is 20 feet. This whole distance is 20 feet. And then we will add the third load, which is the 32 kip, times the slope, which is 12 over 30, times the distance, which will be 16. This drawing is not proportional, but if this whole length is 30 feet and this section is 14 feet, so then that means that this will be 16 feet. And this will give us 28.8 plus 384 plus 204.8, which is a total of 617.6 kips per foot. And this is the maximum positive moment at B. So this is the answer for part 2. But now we also have to solve for the maximum negative moment at B. So we will do the same thing, or this will be the maximum negative moment at B. And we just did the maximum positive moment at B. So we will do the same thing, draw the moment, the influence line for the moment at B, which will be the same as the problem we just did. So we just go ahead and copy the same influence line for the moment at B that we just solved. We said that this was 12. We said that this slope was 12 over 30, and this slope was 12 over 20. So now we can go ahead and draw the load, the moving load. Since we want the maximum negative moment at B, we're going to have to place this moving load in the maximum negative section. And as mentioned before, this is the negative section and this is the positive section. So we will move this here. So the first load will be here, the second load will be here, and then the third load will be here. And again, this is not proportionally, and again, this drawing is not proportional, so we have to really take a look at the distances that are given. In order to solve for the maximum negative moment, we will start off by using this load, which will be, since it's in the bottom, so it will be negative, so we will do minus 32 kips times the slope. So we first have to find what this point is to find the slope. So we will use similar triangles. So we will do the 12, which is here, and the distance for this, which is 30, is equal to, let's call this t, over this distance, which is 20. And we get that t is equal to 8. So this is 8. So then this means that this slope is equal to 8 over 20. So we will multiply this by 8 over 20, which is the slope that we just found, times the distance, which is 20 feet, because this section here is 20 feet. And we know that since this distance is 14 and this whole distance is 20, we know that the second load will be 6 feet from this part. So we now do the other one. So we do minus 32 kips times the slope, which is 8 over 20, times the distance we just figured out was 6 feet. And then for the third load, we would do, this would be in the positive section. So we know that 14 plus 14 is equal to 28. So then we know that the 8 kip load is somewhere here. So we know that, so then we know that this distance is going to be 8 feet. So then we do plus the 8 kips times the slope, which is 12 over 20, times the distance, which was 8 feet. This would be negative 256 minus 76.8 plus 25.6, which equals negative 307.2 kips per foot, which means that the maximum negative moment is equal to negative 307.2 kips per feet. And this is the answer for part 3. And that is problem 1 solved. Now we can move on to problem 2. So problem 2 reads, for the beam shown, use the influence line to compute the shear and moment at C. So we will start off by computing the shear at C. So as we did in the first problem, we would first have to go ahead and draw the influence line for the shear at C. So we can label this, we have to draw this, and we can label this A, B, and C. So now we draw the influence line for the shear at C, which we know this is a total of 1 unit. So then we draw this line and this line. And since we see that this is in the halfway point and is the same distance on both sides, we can assume that this, well, we know that this is 0.5 and this is 0.5. So then we know that the slope is 0.5 over 20 for this line and the same for this side, 0.5 over 20. So now we can go ahead and draw the uniformly distributed load on the diagram. So we see that it's 10 and 10, so it'll be halfway through this line and halfway through this line. So it will look something like this. And this is 10. So then we can go ahead and keep drawing the line here so we can visually see it. So the main difference for this problem is that since it is a uniformly distributed load, in order to compute for the shear at C, we will take the area, and we will take the area of this shaded section. So we will divide this into a rectangle and a triangle for both of them. And as we recall, this is the positive side and this is going to be the negative. So we can go ahead and calculate this area, which will be 10 times 0.25 times 10, and then the area of this triangle is 1 half 10, 0.25 times 10, which this is the base, the height, and the load. But we really don't have to go ahead and calculate this because we can see that this area is going to cancel out this area, so we're basically just going to be adding to 0. This is for the bottom section, but this will also be the same thing for the top section, which is positive. So we know that this will just cancel out and it will add to 0. So we know that the shear at C is going to be 0. And that is the answer for the first part. And now we can move on to the moment at C. So we will go ahead and draw the influence lines for the moment at C. You can label this part A, C, and B. We can go ahead and draw the influence lines for the moment at C, which will look something like this. And once again, as we did in the last problem, we know that this is 1 unit and this is 1 unit as well. So we can call this, and we have to solve for this point that we will label point D. We know that this is the angle A and this is angle B. And if we divide this part, we know that this is angle A and this is angle B. And just like we did in the first problem, we can go ahead and do the same thing to solve for point D. And then we go ahead and add both angles and set them equal to 1. And we get that DC is equal to 10. So we know that this is 10. So we know that this line has a slope of 10 over 20 because this distance is 20. And this will have the same slope, which is 10 over 20. And now we can go ahead and draw the uniformly distributed load once again. So we know that we have to pay attention to the distance that is 10 and 10. So it will be halfway here and halfway here. This is the uniformly distributed load of 10. So we can draw the lines here. We can separate this into two areas and then divide it once again into a rectangle and a triangle for both sides. You can label this area 1, you can label this area 2. Okay, so now we can solve for it by adding the areas together. That we have to know that this point is 5. And then we can solve for area 1 here. We multiply 5 times 10 times the load, which is going to use a 10. And this would be for area 1. And then for area 2, we do 1 half the base times the height times the load to the 5. And we know that this will be the area 2. And you can see that we label this area 3 and area 4. We see that area 1 is the same as area 3 and area 2 is the same as area 4. So we can just multiply this by 2, this whole thing by 2. And we get 750 times 2, which means that the Moment at C is equal to 1,500, and this will be the answer for part 2, and that is the whole problem solved. The main takeaway here is that for uniformly distributed loads, you have to take the area of the shaded area where the uniformly distributed load is at, compared to the point loads that we did in problem 1. Now we can move on to problem 3. Problem 3 reads, for the beam shown, use the influence line to determine the maximum negative and positive shear at C. Also, maximum negative and positive moment at C for a uniformly distributed load of 20 kips per meter. What this means is that the uniformly distributed load can be any length. We can choose a length depending on how we can ensure that we will have the maximum positive or the maximum negative, either shear or moment. So we will start off by doing the positive shear. And the first thing we will do, like the other problems, is to draw the influence line for the shear at C. So we can draw the diagram. You can label this A, C, B, and D. So to draw the shear at C, we know that it's going to have to be a total of 1 unit, and you can see that it's 10 on this side, 10 on the other side, so this will be 0.5, and this will be 0.5 as well. We can finish drawing the influence lines. It will look something like this. Again, this is not exactly proportional, but it's fine, because if we solve for this, we know that this is 0.5, and we can see that's not proportional, but it doesn't really matter. So since we are doing the maximum positive shear at C, and it's a uniformly distributed load of any length, we know that this is going to be positive and this section is going to be negative. So if we want to get the maximum positive shear at C, we have to put the distributed load in the positive section only. So it will be here with a length of 10 meters, because this is 10 meters. You can draw the distributed load. And as we did in the last problem, we know that to actually calculate for this, it's going to be the area of the shaded region, which is this. So to calculate this, we know that it will be 1/2 the base, which is the 10 meters, times the height, which is the 0.5 that we found, times the load. And we get that the maximum positive shear at C is equal to 50. And this is the answer for the maximum positive shear at C. So now we can move on and do the maximum negative shear at C, the negative one. And we will go ahead and do the same thing, which is to draw the influence line for the shear at C, and we have to go ahead and draw it and label this A, C, B, and D. And then we'll have the same influence line that we just did for the first part, which is this part we know is 0.5, and this is also 0.5, and we can finish off by drawing the influence line like this and like this. And we saw that this is also 0.5. So now we are told to calculate the maximum negative shear at C. So it's going to be the same thing. We know that this is the positive and this is the negative. So if we can be any length, we know that if we want to make it the maximum negative, we will draw the distributed load on top of each negative section, which will be in this part and in this part. So we know once again that we have to calculate the area of the shaded region. So we have to do, so this will be negative because it's in the bottom. So it'll be 1/2 base times height times the load. And then once again for this part will be, I already added the negative. So it'll be 1/2 base times height times the load, which will mean that the maximum negative shear at C is equal to negative 100. And that is the answer for the maximum negative shear at C. Now we can move on and do the maximum negative moment at C. So as always, we start off by drawing the influence line for the moment at C. So we have to draw the diagram first. And we label this part part A, B, C, and D. And we draw the influence line for the moment at C, which will look something like this. And once again, we're going to want to find this part, which we can label E. So we can label this angle A and label this angle B. And we can draw the parallel line here. And this will be angle A. And this will be angle B. Yeah, angle B. So then we know that angle, and we know that this again is one unit as well as the other side. So this would be angle A is equal to EC over 10, and angle B is equal to EC over 10 as well. So then we add these two angles and set them equal to 1. And we get, if we solve for EC, we get that EC is equal to 5. So we put this as 5. And if we use like the triangles, we can find that this is also 5. So now since we want to do the maximum negative moment at C, we have to do the same thing that we did for the shear. So we know that this part will be positive and this will be negative, so we will want to draw the uniformly distributed load on the negative section, which will be here. So we have to calculate the area of the shaded region, which will be 1/2 base, which is the 10 meters, times the height, which is -5 meters, times the load. And we get that the maximum negative moment at C is equal to negative 500. And that is the maximum negative moment at C. So now we can calculate the maximum positive moment at C, which will be the same thing. We have to draw the influence line for the moment at C, which is the same as the one we just did. So I can just go ahead and quickly draw this. A, B, C, and D. And the same influence lines that we just did. And we saw that this was 5, and this was also 5. So now for the maximum positive moment at C, we have to know again that this is positive and this is negative. So we won't want to draw the uniformly distributed load on top of the positive section, which this whole section is positive, so we will draw the uniformly distributed load on top of this. So we know that the shaded area that we're going to calculate is this whole area. So I went ahead and divided this into two areas just because it's easier to see. So this is area 1 and this is area 2. So it's 1/2 base, 10 meters, times the height, which is 5 meters, times the load, which is this. And then I went ahead and multiplied this by 2 since there's 2 of the same area. And we get that the maximum positive moment at C is equal to 1,000. And this is the answer for the last part of this problem. And this is the whole problem completed. So that was 3 problems completed that included moving loads and uniformly distributed loads, and thank you.